Alright, so applications of differentiation. So besides residuals, or not residuals, but differentials and other things, we can understand a few concepts of applications of differentiation. So intuitively, we have to understand what a minimum and maximum is. So that's the first idea. You should have learned this in Algebra 2 or pre-calc, ULIS if you have taken pre-calculus. But essentially, on a curve, a maximum and minimum is well, there's two types of maximum and minimum. There's absolute maximum, which essentially means the highest point on the graph, or the lowest point on the graph, the absolute maximum or the absolute minimum. So, for example, here, if this went on infinitely, there is no absolute maximum or absolute minimum because it gets arbitrarily large. Um, so there's no way for you to be able to find an absolute maximum because there will always be a point that is greater than set absolute maximum. So the difference is if you have a parabola like this, you can say that this is the absolute minimum because there's no point that is smaller than this point right here. So what happens if you have a cubic function like this? Well, these points right here is what we call the relative minimum. Or relative maxima and relative minima. So essentially, what these points mean are, and you'll see minima, or you'll usually see the word extrema as well. And the reason why they say extrema is because extrema is kind of a neutral term. It doesn't either mean maxima or minima. So on this graph, I could say there's two extrema, but I can only say there's one maxima and one minima. Because the sums of the maxima and minima are equal to the number of extrema. So that's pretty logical there. So let's define the terms. So what is an absolute maxima? So I'll just say AM for absolute maxima, and that's if f of x is greater than, or f of a is greater than f of x for all x in D. Essentially stating that the output or the value on the y-axis is greater than everything else on the graph. So if you have like a parabola here, then this f of a is greater than any other f of x you can put. So pretty simple and logical there. So how would you define the rest of the points? Well, being logical then the relative minima or relative or the absolute minima would be f of a is smaller than f of x for all x and D. So notice how we have a greater than or equal to sign. Surprisingly, if you have a horizontal line, any point on here is considered a absolute or a relative minima or maxima, simply because we get to the definitions of critical points later on, which is how they're sort of defined. So note that if one point is equal to the rest of all the other points, it is also considered, I think, a relative minima or maxima, not an absolute maxima. So yeah, f of a greater than f of x for a near x is considered, or x near a, same thing. If x is near a, then a is near x, is absolute minima and or absolute maxima, and in the same way, f of a is less than f of x is for x near a as well. Now, again, I don't like these arbitrary definitions, or not these arbitrary, these ambiguous definitions, because what concludes x near a? For example, is an interval of 0.5 considered close, or an interval considered, or is that considered large? So what does the term near really mean in math? And unfortunately, my calculus book doesn't define it as such, but I'm sure it has something to do with the precise definition of a limit and epsilon delta proofs. But that's beyond the scope of the course. So if you're ever curious on that, you can do some research, but there is no true definition of near, at least in the mathematical sense. So there's logic there. So let's do a little practice problem here, and I'm going to draw a curve, and you're going to be able to differentiate the points. So actually, let's not say that it goes on forever. Let's just put an endpoint here. The reason I put endpoints here is so that you don't assume that the function gets arbitrarily big or arbitrarily small. So there is an absolute maxima and absolute minima. Well, let's go for the obvious ones. The absolute maxima is the top one here, so that's AM. And this is the absolute minima, so that's a how would I say minimum without having the same one? Let's just say mi to differentiate the two. This one looks like a pretty close contender, but this one is slightly lower on the graph. This one would be a relative maxima, and this would be a relative minima. So again, I don't know what x near a means. It doesn't really make sense to me, but I think the definition holds regardless of how small you pull the two. So for example, if we have a graph that looks like this, I would say all these points are relative maxima, even if they differ by 0.0002 on that scale. So I guess, yeah, relative minima does apply, but I guess the closer definition would be any point that is greater than the following point or the previous point, which would maybe be a more precise definition than x is near a. But again, that's just my thoughts. It's nothing mathematically proven. Oh, and that would be a relative minima as well. The one on the left. The one on the left. So let's take f of x equals cosine x, and we'll find maximum or minimum. So this is going to require a little bit of not trigonometric, I guess. The intersection between geometry and algebra knowledge and calculus, theoretically. So let's say we have a cosine graph, and a cosine graph looks like this. I hate drawing cosine graphs, but here would be 0, here would be pi over 2, here would be pi, so on and so forth. Here would be negative pi over 2, and here would be negative pi. So a pretty simple cosine graph here. So technically, there is no absolute maximum here, because as we know, there is no one point that is greater than the rest. But we do know one thing, and we know that cosine is periodic. So the period would be 2 pi over b, which is the coefficient behind the input. But fortunately for us, the cosine input is 2 pi. So that means every 2 pi the values repeat. So all we need to do is find one minimum here, or a maximum here, and the question asks for any maxima or minima. So max or minimum. Well, max would just be the repeated top values for the y. So this one is at 1, as we know from our trigonometric knowledge. So it'd be 1 comma n 2 pi, essentially where n is an integer. And it can also be 0 as well. And in the same way, a minimum will be the exact same thing, except we start at pi over 2, or not pi over 2, pi. So pi plus n2 pi, comma, or pi plus n2 pi, comma 1 with the same restriction. So simple logic, pretty easy stuff. So, yeah, you know what? We'll do another one where we'll take y equals x squared. So find the minima here. Well, looking at the graph, you would just assume the minima is here. It gets tricky to find the actual minima without using a calculator, typically, because how would you evaluate what this lowest point on the graph is? For us, it's easy for a quadratic like x squared, because we can apply the distance, or we can apply the formula, which is negative b over 2a. Which finds us the vertex point, which is either the minima or maxima, and b is 0. So we know that it's at 0, plug that back in here, 0, 0. But how would we find it algebraically for a tough function like, let's just say whatever this is, y equals x cubed plus x squared plus 4x plus 15.78. Be pretty hard. I'm not sure if this graph is actually accurate of this approximate polynomial. Probably not, but something like that. How would you find the minima? Now, it gets difficult here. So typically, quadratics are the only graph you will be asked to find the minima or maxima in pre-calc classes, because you don't go over applications of derivatives. But since we're here in calculus, it's easy for us to do so. So let's take Fermat's theorem, which Fermat's theorem is really logical. Actually, if you look at Pierre Fermat's work, he is really, really, really smart. In fact, he wrote Fermat's last theorem, which states that the Pythagorean identity doesn't work for any integers past 2, which is crazy because he proposed that back in the 1700s, and he said he had a proof so marvelous he couldn't write down it. He couldn't write down any of it, or if you were to write it down with like 500 pages, it wouldn't be able to fit. Um, so he never sent the proof out because it would be impossible to write. Um, and people thought he was bluffing until a few hundred years later that his proof or a proof was discovered, and his theorem ended up to be true. But that's beyond the point. So Fermat's theorem states that if f has a local or maxima or minima at C, so if you don't understand notation, like I kind of do, just I'll try to explain it um, as in layman terms, essentially. So like I know these things can be confusing, but trust me, it's not that hard to understand. So I'm just gonna explain this graphically. So let's just say that we have a parabola right here. If the function has a local minima here, then the derivative at that same exact point is gonna be equal to 0. So essentially, if f of 4, if f of 4 is equal to a max, then f prime of 4 has to be 0. So that's all that means. Essentially, a minimus point will have a derivative or rate of change of 0 at that point, which is logical because take a parabola right here. We have a minima here. The derivative is going to be 0 at that point. So that's pretty logical and pretty simple stuff. So a critical point is a number C in the domain of f such that, you know what, this one might be a little bit easy or difficult to understand. But actually it's not difficult at all. A critical point is essentially when f prime of c is equal to 0, or f prime of c doesn't exist. But I also think that a critical point, in a more broad term, I believe is when the function signage changes. So, for example, one second. Yeah. So, critical point is essentially when f of x or f prime of x does not exist. So, for example, let's take x squared, or let's do something a little bit more complicated, such that when we take the derivative, the root is not going to be 0. We can apply the power rule here, which will give us 2x plus 4. So we have to solve for 0, and we realize that x equals negative 2 will give us 0. So that means negative 2 is considered a critical point. Now, what does it mean by it doesn't exist? Well, that's pretty simple as well. Let's just go over the derivative of f of x equals 1 over x, which is essentially just negative x, well, that wouldn't work actually. Let's try something a little bit easier. Let's do tan x, and if we take the derivative of that, we get secant squared x, and secant squared x is equal to 1 over cosine x squared. So when is cosine x equal to 0? That's pi over 2, so pi over 2 is considered a critical point, even though that entire function doesn't evaluate to any point. So that's the logic there, and that's all we know. So now we get to someone else's, well, think about it logically this way, and I know it doesn't hold for everything. If f prime of x is equal to, if f of c equals min f prime of c equals 0, is it not logical to assume that if f of prime equals 0, f of c equals min or max? I should have probably put extrema, but that's fine. And in typical logic classes or introduction to logic classes, you know that this is considered fallacious, that this is not always the case. But in math, it does turn out that a derivative that is equal to 0 is typically equal to the extrema. So not all the time, there are some rare exceptions. But essentially, if there's a critical point that makes the derivative equal to 0, then the f of c will be the minima or maxima. So that's how actually the quadratic formula, vertex formula, was found. So for example, any second degree polynomial here, if you take the derivative, that becomes 2ax plus b. And solving for x, you get x equals negative b over 2a. So, but you can apply that to anything. So let's do ax cubed. I don't know if there's a cubic formula. There probably is, because it just converges to a polynomial. Let me see if I could solve it right now. Plus cx plus d. Take derivative, you get 3ax squared plus 2bx plus c. You could probably factor out a 3 ax squared plus 2b over 3ax plus. There probably is a solution, but it's probably a little bit more difficult because you'll need to use the quadratic formula. But yeah, you can calculate derivatives there. So yeah. So as I've said before, if f prime of c equals 0, then the critical point will typically have a minima at that point. Again, I don't think my book states it as direct as that, but let's do a practice problem, and we'll do f of c, where f of x is equal to x cubed minus 3x squared plus 1. F prime is going to then be equal to power rule, so 3x squared minus 6x. And is that a plus 1? Yeah, it's a plus 1, so it just falls out. So my book also restricts the domain between negative 1/2 and 4, probably because they don't want too many minima or maxima. So it asks, find the absolute maxima and minimum values. So if we take the derivative, we have that. So we have to find the critical point. Let's factor out a 3 to get x squared minus, or actually let's factor out 3x. 3x to get x minus 3, or x minus 2. So we know the critical points are x equals 2 and 0. We plug that back in here, and these both fall into the domain of here, so we can test both. 2 cubed minus 3, 2 squared plus 1 is going to be equal to 8 minus 12 plus 1, so that's going to be 5. So, sorry, that's negative 3. What am I doing? Okay, so, because that's a negative. Yeah, negative 3. So that means there is an extrema at negative 3. And then we're going to do the other one, and we plug 0 in to get that f prime of 0 is equal to 1, and f prime of c, or 2, is going to be equal to negative 3. But here's the question. How do we know if it's an extrema, or if it's a maxima or minima? And that we can't know until we get to the second derivative test later on. So you'll have to plug this into a calculator or graphing calculator and see whether that's an absolute maxima or minima. So we'll learn about concavity up and concavity down using second derivative tests. But as you know, that's a little further down the line than this. The next chapter is going to be Rolle's theorem and other stuff. Rolle's theorem and the Cauchy's mean value theorem, which they actually use to prove L'Hopital's rule. So that's the logic behind 4.1.